Hello, welcome to the second unit, matrix eigenvalue problem and quadratic forms. In this lecture, we are going to see how to reduce a quadratic form to canonical form by using orthogonal transformation. In the last session, we have seen what is meant by orthogonal transformation. We have seen already what is transformation followed by orthogonal transformation. So transformation is nothing but if I take y equals to ax, we are transforming x with the help of the matrix A to y. Whenever that matrix A is an orthogonal matrix, we say that it is an orthogonal transformation. So here, to reduce the quadratic form to canonical form, which is already we discussed what is canonical form. So it is also known as sum of the squares form or normal form or principal axis form. So to reduce the quadratic form to canonical form by using orthogonal transformation, so this is the procedure we have to follow. So what is the procedure is here? First write the coefficient matrix associated with the given quadratic form. We have to write first the coefficient matrix associated with the given quadratic form. Next, find the eigenvalues of the matrix A. Next, we have to find the eigenvalues of the matrix A. Then write the canonical form using lambda 1 y1 square plus lambda 2 y2 square plus and so on plus lambda n yn square. Next, form the matrix P containing the normalized eigenvectors of A. So in the second step, we calculated the eigenvalues. So corresponding to the eigenvalues, we have to calculate the corresponding eigenvectors. Once you got the eigenvectors, you have to check it whether they are pairwise orthogonal or not. If they are pairwise orthogonal, then next is you have to construct a matrix P which is normalized eigenvectors of A. So this is known as the P is known as the normalized model matrix. P is just model matrix. So P cap stands for the normalized model matrix. Then X equals to P cap Y gives the required orthogonal transformation. So this gives the required orthogonal transformation which reduces the quadratic form to canonical form. So these are the simple steps we have to follow. So first, for the given quadratic form, write the coefficient matrix. Next, find the eigenvalues of that matrix. Next, find the eigenvectors of the corresponding eigenvalues. Then check it whether they are pairwise orthogonal or not. If they are pairwise orthogonal, then normalize those vectors and construct the normalized model matrix. Once in your hand the normalized model matrix is there, then you can use X equals to P transpose Y to get the corresponding orthogonal transformation. So which is required to reduce the quadratic form to canonical form. So we will go through this entire procedure by using one problem. So if you look at this problem, what he is asking is find the orthogonal transformation. So he wants the orthogonal transformation which transforms the quadratic form x1 square plus 3x2 square plus 3x3 square minus 2x2 x3 to a canonical form. So he's asking what is the transformation is there, that is the orthogonal transformation which transforms this quadratic form to canonical form. Next, he is also asking determine the index, signature and nature of the quadratic form also. So the index, signature and nature of this quadratic form also he is asking. So now the quadratic form is supplied to you. So first job we have to do is we have to write the associated symmetric matrix for the given quadratic form. So that's the first step. So here the symmetric matrix A, we are naming that one as A, the symmetric matrix A associated with the given quadratic form. This one is A equals to, how to write the symmetric matrix? First, write the coefficients of squared terms along the principal diagonal. So what are the square terms here? X1 square, X2 square, X3 square. So their coefficients are 1, 3, 3. So 1, 3, 3 comes along the diagonal. Next, x2, x3 is there. So x2, x3 coefficient is -2. So divide this into two parts. One part serves for second row, third column. Another part serves for third row, second column. So -2, if you split it into two equal parts, you will get -1, -1. So 1 -1 serves for second row, third column, here this entry. And third row, second column, the next half part, -1. And the remaining terms are missing here, right? They are not supplied, therefore automatically you have to fill up the remaining entries with 0. So this is the matrix. Once you got the matrix, just ensure that whether it is symmetric or not. So clearly, if you take its transpose, you are going to get once again the same matrix. Okay, so that's the first step, writing the symmetric matrix associated with the given quadratic form. Next is we have to calculate the eigenvalues. To calculate the eigenvalues, write the characteristic equation. So the characteristic equation of this is that a minus lambda equals to 0. From that you will get this cubic equation. So solve this cubic equation. So we will get the roots is lambda equals to 1, 2, 4. So these are the eigenvalues of the matrix. So at any point of time, if you have doubt about these eigenvalues, then you can check it. The sum of the eigenvalues, if you add it, 4 plus 2 plus 1, how much? 6, which is equals to trace of the matrix. And similarly, if you calculate the debt, calculation of debt is very easy here. So what is the debt value? You will get 3 into 3. So you will get the debt is 9 minus 1, 8, right? So the debt is 8. Here also, if you see the product of the eigenvalues, 4 into 2, 8, 8 into 1 is 8. So therefore, these are the correct eigenvalues, just to ensure that, right, whether they are correct or not. If you do a mistake here itself, the whole problem goes wrong. Okay. So we got the eigenvalues here. Now get the corresponding eigenvectors. We know how to calculate the eigenvectors. So for lambda equals to 1, this is the first eigenvector we got, because you know the procedure how to get the eigenvectors, right? So directly I calculated the eigenvectors for the corresponding eigenvalues. So for lambda 1 equals to 1, we got 1, 0, 0. For lambda 2 equals to 2, 0, 1, 0. For lambda 3 equals to 4, 0, 1, minus 1. So the choice is yours. You can choose any k value here. You can choose k is 1 here, you can choose k is 3 here, you can choose k is 100, any values. But for the sake of simplification comfort, we are choosing k in all the three cases as 1, 1, 1. Therefore, the eigenvectors we got is 1, 0, 0, 0, 1, 1, 0, 1, minus 1. Once you got the eigenvectors, the immediate job you have to see is check it whether they are pairwise orthogonal or not. No doubt they are linearly independent. That is obvious, they are linearly independent. Next, you have to check it whether they are pairwise orthogonal or not. So for that purpose, what you have to do, multiply x1 transpose x2. 1 into 0, 0, 0 into 1 is 0, 0 into 1 is 0. So it is 0. Similarly, 0 into 0, 0, 1 into 1 is plus 1, 1 into minus 1 is minus 1. Gets cancelled, 0. First and last, x1 and x3. 1 into 0, 0, 0 into 1 is 0, 0 into minus 1 is 0. So here all are 0. So they are pairwise orthogonal. Suppose if they are not pairwise orthogonal, it is our job, we have to make the vectors as pairwise orthogonal. That type of problem we already discussed in the last video. Okay. Now the vectors what we got is they are linearly independent as well as pairwise orthogonal. Now we have to construct the model matrix. So if you construct the model matrix P by taking these vectors as column vectors, that is P equals to x1, x2, x3, P equals to x1, x2, x3. So that is known as the model matrix only. That is known as model matrix. But we want the normalized model matrix. Therefore, the normalized eigenvectors we have to calculate. So for that, what we are doing is here we are normalizing this. That means I am dividing this vector with its norm, and the second vector also with its norm, and the third vector also with its norm. So x1, x2, x3. So I am dividing all these three vectors. So norm of first one is 1, 0, 0. Second one is 0, 1 by root 2, 1 by root 2. Third one norm is 0, 1 minus 1. Square root of 0 is 0. 1 is 1 square is 1 minus 1 square is plus 1. So which is root 2. So I divided each vector with its norm. So we got 1 0 0 here, the first one. Second one is 0 1 by root 2 1 by root 2, 0 1 by root 2 minus 1 by root 2. So once you got the norms, then construct the normalized model matrix, which we are representing with P cap. So this is the normalized. So this is first vector, second vector, third vector. Then calculate its inverse. Because this is a orthogonal matrix, its inverse is nothing but its transpose only. So take its transpose. And here we taken its transpose and we brought 1 by root 2 outside. So this is the P inverse. Next, P inverse AP we calculate. Then P inverse is this, and A is the given vector, given matrix, and P cap is this one. So if you take its product, we got it is D. So clearly, if you look at D, the diagonal matrix, the leading principal diagonal entries are 1, 2, 4, which are nothing but the eigenvalues. Now we have to write the quadratic form, canonical form we have to write. So we know that the quadratic form is Q is X transpose AX. Now I am using the transformation X equals to P cap Y. So instead of X, if I put P cap Y, then if you take its transpose, Y transpose, P cap transpose, A P cap Y. So P cap transpose, A P cap, this one just now we got, it is D. So Y transpose dy you will get. So therefore the canonical form is Y transpose means Y is what? Column vector y1, y2, y3. So its transpose is y1, y2, y3. D is just now we got the diagonal matrix, and Y is y1, y2. So this is the canonical form. So once you got the canonical form, so writing index, signature and nature is very easy. All the eigenvalues are positive, therefore nature is positive definite. Index is the number of positive square terms are 3, index is 3. Signature is the difference between the number of positive square terms and negative square terms. So in this case, only 3 positive square terms are there. There is no negative square terms. Therefore, 3 minus 0 is 3. So index is 3, signature is 3, and the nature is positive definite. And he is asking what is the orthogonal transformation. So the orthogonal transformation is X equals to P cap Y. X is what? X1, X2, X3. P cap we calculated already. Y is Y1, Y2, Y3. So if you compare, X1 we got Y1, X2 is this, and X3 is this one. So this is the required orthogonal transformation. So this is the way of reducing the quadratic form with the help of orthogonal transformation. So it is, which is very simple. Okay. So it is easy also. So I am Srikanth Reddy. Thanks for watching. I will meet you in the next video.